So when maybe you or somebody else creates an AGI system and you get to ask her one question, what would that question be?
What's outside the simulation?
We're living in a computer simulation. The Matrix is real. Our entire universe is just code running on some alien supercomputer. If you've spent any time on the internet in the last decade, you've heard this claim 1,000 times. Elon Musk says the odds we're in base reality are billions to 1. Philosophers like Nick Bostrom have made mathematical arguments for why we're probably simulated. Even respected physicists are taking this idea seriously. Here's the problem. They're all wrong. Spectacularly, embarrassingly wrong. And I can prove it using nothing but basic physics, information theory, and mathematical logic that anyone with a high school education can understand. Welcome back to the Cosmic Codex, where we separate science from science fiction using actual science. Today, I'm going to systematically demolish one of the most popular pseudoscientific beliefs of our time and show you why the universe is definitely, provably, not a computer simulation. For those of you who already believe we're living in the Matrix, it may feel like I'm trying to offer you the blue pill, but that's not the goal. Look, I know what's about to happen. The moment I say simulation theory is wrong, half of you are going to smash that dislike button faster than Neo dodging bullets. The Matrix fans are going to crucify me in the comments, the Elon Musk disciples are going to tell me I don't understand advanced physics, and somewhere a philosophy student is already warming up to type a very angry essay about why I'm destroying people's hope. But here's the thing. I'm not here to attack your beliefs or ruin your favorite movie. I'm not trying to be some dream-crushing buzzkill who hates fun. Hell, I love The Matrix too. It's a brilliant film. But there's a massive difference between enjoying science fiction and mistaking it for actual science. So before you click away or start furiously typing in the comments, I'm asking for just one thing. Give me 12 minutes. Watch the entire argument. Let me show you the mathematics, the physics, the logic. Don't judge the conclusion before you've seen the evidence. Because here's what's really wild. The actual universe, the real reality we're living in, is so much more incredible than any simulation could ever be. And I can prove that too. I'm not here to take away your sense of wonder. I'm here to redirect it towards something even more amazing, the genuine, provable, mind-blowing truth about what reality actually is.
You've been living in a dream world, Neo. This is the world as it exists today.
Let's start with the short version. The simulation hypothesis says we might live inside a computer simulation created by some advanced civilization. It's the Matrix, but without leather, and probably worse lighting. The modern, rigorous version of this idea was framed as a trilemma. Either 1, almost all civilizations die before they can build ancestor simulations, or 2, advanced civilizations have no interest in simulating ancestors, or 3, we are almost certainly living in a simulation. If you reject 1 and 2, you're pushed to accept 3. Elegant, unsettling, and deliciously simple. But does simplicity equal truth? Not always. Before we judge, let's ask the right questions. What assumptions does the hypothesis rely on, and can those assumptions be tested? There are 3 big assumptions hiding behind the idea that we're simulated: computational feasibility, philosophical substrate independence, and the statistical argument about observers. I'll take each in turn and throw in a few numbers because people in lab coats like things with digits. First, computational feasibility. Can a civilization actually simulate a universe, or even just a pace of life like Earth with people and weather and coffee stains, without inventing magic? A lot of the drama collapses once you do some back-of-the-envelope math. The human brain is often the benchmark. If you can simulate a brain, you can simulate minds. A conservative neuroscience estimate gives us roughly 10 to the 11th neurons and about 10 to the 14 synapses for a human brain. If we store 1 byte per synapse, tiny, tight, and optimistic, that's 100,000 gigabytes, about 91 terabytes. That's one person's memory map at a synapse resolution level. Multiply by millions or billions of simulated people, and you're well into exabytes and beyond. If each synapse needed more complex state, milliseconds of potentials, ion channel states, detailed biochemistry, the cost skyrockets. But raw storage isn't the whole story. To run a brain, you need operations per second, synaptic updates, spike propagation, short-term plasticity. If each synapse updates on average 100 times per second, reasonable for many networks, then one brain needs about 10 to the 16th operations per second. That's 10 petaflops of sustained computation per person. A lot, but not unattainable in principle for an industrial civilization with huge computational infrastructure. The kicker is scale. Simulating billions of brains plus entire planetary environments in fine detail is an astronomical, pun intended, computing problem.
Now, a reality check. There are physics-based limits on computation. Landauer's principle tells us there's a minimum thermodynamic energy cost to erase information, about 2.87 times 10 to the minus 21 joules per bit at room temperature. Sounds tiny, and it is tiny, but multiply that by the billions of bits you'd flip per second, and you get a real power bill. Still, thermodynamic limits are not showstoppers. They set bounds, not impossibilities. In short, computationally hard may be expensive, but not obviously physically impossible. So an advanced civilization could plausibly have the hardware for simulations, if they want to build it. Second assumption, substrate independence of consciousness. This is more philosophical than physical. It supposes that consciousness can be implemented on any sufficiently complex computational substrate, silicon, biological wetware, whatever. If true, emulating the functional structure of a brain should produce the same conscious experience. If false, then even a perfect simulation of our atoms may not produce conscious beings. This is a tricky philosophical knot. There's no experimental proof either way. It's a metaphysical leap we often smuggle into these debates. We assume minds are software, not irreducibly tied to carbon wetware. Third assumption, the statistical argument, often called the simulation argument proper. The idea is simple. If A, advanced civilizations can run many ancestor-type simulations, and B, they do run a huge number of them, then the number of simulated conscious beings could vastly outnumber biological ones. By random sampling, you'd probably be in a simulation. That move converts computational plausibility into probabilistic inevitability. The great weakness is that it replaces one unknown with another. We don't know whether future civs will run ancestor sims, and if they do, how many? Large numbers amplify uncertainty. They do not resolve it. Okay, fun so far, but let's ask, can we test the idea scientifically? At first glance, no. A perfect simulation would be made to be indistinguishable from base reality. But the clever people don't stop there. Scientists and philosophers have proposed possible empirical signatures, subtle cracks that a simulated universe might reveal. I'll run through 3 main testable predictions that have been discussed in the literature and what they mean. Test 1. Discretization of space-time. If a simulation runs on finite resolution hardware, the simulated space might have a smallest unit, a lattice spacing, analogous to pixels. That could show up as violations of Lorentz invariance, or energy momentum conservation at extreme energies. In the real world, we look for these signs in ultra-high energy cosmic rays, and in the behavior of gamma rays. If particle energies show unexpected cutoffs or preferred directions aligning with a lattice,
that could hint at an underlying grid. In practice, tests are hard and signals ambiguous. Physics experiments thus far show extremely tight Lorentz invariants, so this test has not revealed smoking guns. Test 2. Computation-limited anomalies, rendering shortcuts. In complex graphics, video games don't render what you're not looking at. Could a simulator save resources by rendering detail only when observed? That idea predicts observer-dependent decoherence, or improbable correlations at the edges of observability. In quantum mechanics, measurement already plays a weird role. Some have suggested that looking for observer-dependent collapse anomalies could offer clues. So far, quantum experiments remain well described by standard quantum theory, but quantum foundations are subtle and contested. Not an obvious smoking gun, more like a philosophical eyebrow raise. Test 3. Statistical signatures in natural randomness. If the simulation uses pseudo-random number generators for large-scale stochastic processes, certain statistical fingerprints might appear. Non-ideal randomness, patterns, or repetitions. For instance, if very large-scale cosmological fluctuations or extreme events show unexpected regularity, that could be a hint. But natural processes and chaotic systems produce patterns too, and finding a pattern is not the same as finding a program. It's easy to mistake structure for intention.
So the empirical routes exist, but all are difficult and ambiguous. Now some math to show the sort of reasoning scientists actually use when testing these ideas. Remember our earlier synapse numbers? 10 to the 14th synapses, 91 terabytes at 1 byte per synapse. If we require, say, 100 updates per second across those synapses, that's about 10 to the 16th updates per second, roughly 10 petaflops. Multiply that by 1 million simulated people, tiny compared to Earth's population, and you need 10 to the 22nd operations per second. Those are monstrous numbers. The upshot, if the future civilization is running such sims, either they have unfathomable compute or they limit the simulation in clever ways. Coarse-grained physics, selective fidelity, or partial realism. That gives us a clue. If simulations are being run, they're probably not perfect atom-for-atom recreations of entire planets. They're optimized. Which brings us to a powerful critique, Occam's razor. The simulation hypothesis often flips Occam on its head. Instead of positing a simple, elegant underlying reality, it posits a more complex infrastructure behind everything. Why not accept the simpler explanation that reality is real unless there's good reason to posit a simulator? Proponents counter that the simplest statistical expectation given multiple ancestor simulation instances leads to the simulation being more likely, but that argument depends on debated priors. Bayesian inference is great, but garbage in yields garbage out. Another philosophical crack appears in the idea of ancestor simulations themselves. If the goal of these simulations is to study history, they must be sufficiently accurate to produce the phenomena of interest. But many scientific phenomena are emergent and sensitive to tiny differences. If you fuzz out the microphysics to save compute, you might miss the very effects you'd want to study. So it's plausible that advanced simulators either simulate only what's needed, or they simulate at high fidelity but only for a tiny sample. Both options undermine the "we are almost certainly simulated" probability boost.
Let's talk about falsifiability, because that's the heart of scientific respectability. A hypothesis that cannot be disconfirmed is not science, it's metaphysics. The simulation hypothesis can be made unfalsifiable by building simulators who intentionally erase evidence of their own existence inside the simulation. That's cheating. But if we restrict ourselves to the weaker claim that a simulation might leak detectable signatures, then it becomes at least partly testable. Look for Lorentz violations, search for anomalous cosmic ray cutoffs, examine statistical randomness in the cosmic microwave background, and scrutinize the quantum measurement problem. So far, no convincing leaks. Now for a thought experiment to sharpen intuitions. Imagine a future civilization that wants to study your neighborhood in detail. Not you personally, but social dynamics at the block level. It wants to run a million Monte Carlo histories to understand how neighborhoods evolve. It will likely simplify, approximate molecules, simulate weather with fluid approximations, and model people as agents with compressed internal states. The simulation will be optimized for the questions the civilization cares about. That implies many simulations would be low fidelity in everyday details. You being conscious matters only if the simulation architecture preserves whatever substrate independence is required. That reduces the probability that your precise reality is a perfect high-res copy.
I promised jokes sprinkled in. Here's one. If we are in a simulation, at least the lag is not our fault. And if you see a frame drop, don't blame your ISP. Blame the simulator's GPU. Back on the serious channel, let's discuss the astronomical number objection. A common reaction is there could be a trillion simulated minds, so probability skyrockets. But quantifying that trillion requires assumptions about future demographics, values, and ethics. Will advanced civilizations simulate suffering? Will they have reasons to run ancestral simulations? They might consider it unethical, or they might find simulations boring and prefer other research. These are empirical, sociological questions about hypothetical civilizations, not physics. We can't reliably assign probabilities to them. What about consciousness as evidence? Some argue that subjective experience feels real and that such realism indicates a base reality. But that's a philosophical move. Your experience doesn't give a meta-ontological certificate. If you're simulated, you'd still have vivid experiences. That's the creep. The simulation hypothesis is consistent with virtually any observation you make inside the simulation, which makes falsification tough. So what is the best scientific stance? Skeptical, curious, and cautious. Simulation theory is a serious philosophical and occasionally scientific conversation starter. It has motivated clever empirical proposals, which is good. The correct scientific attitude is to test the testable and admit the limits of the rest. If future experiments found Lorentz violations implying a lattice scale, or if cosmic ray spectra showed telltale anisotropies tied to a grid, that would be revolutionary. Until then, the hypothesis sits in a gray zone, interesting enough to discuss, but not yet evidence-backed. So there you have it. Simulation theory isn't just wrong, it's spectacularly, mathematically, thermodynamically impossible. We've dismantled the computational arguments, destroyed the physics claims, and shown why every piece of evidence has much simpler explanations. But here's the beautiful conclusion. We don't need to be simulated to be special. We're not NPCs in some cosmic video game. We're patterns of stardust that became conscious enough to contemplate our own existence in a universe that's genuinely, provably real. And that's not just amazing, it's the most incredible thing that's ever happened in the history of the cosmos. Now, I know some of you are probably thinking, but what about this specific argument? Or you didn't address that particular study. And you're right, there's always more to discuss. That's exactly why I want to hear from you. Drop your thoughts in the comments below. If you've got criticisms of my arguments, bring them on. I love a good scientific debate. If you think I missed something important, let me know. If you've got additional evidence that supports or challenges what we've discussed, I want to see it. And here's something cool. I've opened up the community tab for all subscribers. That means once you hit that subscribe button, you can post images, share research papers, upload diagrams, or start discussions that dive even deeper into these topics. Think of it as our own little scientific forum where we can really dig into the evidence together. Whether you agree with me or think I'm completely wrong, your voice matters in this conversation. Science isn't about one person being right, it's about collectively getting closer to the truth through evidence, debate, and rigorous analysis. So smash that like button if you enjoyed having your assumptions challenged by actual mathematics. Subscribe to the Cosmic Codex for more reality-based, reality-breaking content. And don't forget to check out that community tab. I genuinely want to see what evidence and arguments you bring to the table.
Because at the end of the day, we're all just curious humans trying to figure out this incredible universe we live in. And whether we agree or disagree, that shared curiosity is what makes us human in the first place. Until next time, keep questioning everything, but always demand the evidence to back it up.